Okay, so in these videos we'll be talking about transistor device physics, and we'll take a qualitative view, right? These videos are gonna be divided into three parts. The first part is gonna talk about PN junctions. We're gonna be talking about intrinsic silicon, then what happened when we dope silicon, then the mechanisms for carrier motion, the mechanism for electron and hole motion. Then we're going to be talking about what happens when we put an N-type material and a P-type material together. Then we're going to see how that turns out to be a diode, the one that we use in our experiments. Then we're going to talk about the non-idealities of the diode, such as the leakage current. Then we're going to finally look at the effects of the effects that happen in a PN junction, such as capacitance, and that's going to be the last part of that section, which is going to be the capacitance of a PN junction. For part 2, we're going to be talking about MOSFETs. So we're going to start with the MOS capacitors, sometimes called also the gate capacitance. And then we're going to talk about the MOS transistor in a strong inversion, which is how we use it. And then we're going to look at the MOSFET behavior under different applied biases. Then we're going to look at some of the non-idealities, such as the channel length modulation, the body effect, and finally we'll talk briefly about small signal analysis and what it really means, how some people get confused. The part 3 of these videos is going to talk about BJTs, or bipolar junction transistors. We'll start off by talking about why is the reason for using BJTs, the advantages, the disadvantages. And then we'll talk briefly about, we'll give a little story indicating the basic operation of a BJT. Again, I'm going to give you a qualitative view of how these devices all work, so that later on when you look at the formulas you can totally see where they are coming from. But this is not going to include any equations or anything like that. But I think it's sometimes more important than just plugging numbers. So here it goes. Okay, so let's talk very briefly about semiconductors. Okay, so in this case we'll be talking about silicon. Right? There is other elements that sometimes they use to make transistors and diodes, like germanium, to get different threshold voltages, but we'll focus on the most common now, which is the silicon. And then we'll be talking about intrinsic and doped silicon. So silicon is a crystal lattice that is very stable, and then what that means is that it doesn't conduct electricity very easily at low temperatures. However, it's very thermally affected in that as you increase the temperature, there are more thermally generated carriers, which means that, you know, if you put a potential through it, you're going to get some current flowing. All right? So that's something we use. But okay, so let's draw the model for silicon, for intrinsic and doped silicon. So here's a simplified model of how the crystal lattice will look. And as you can see, there are no free carriers, right? Everything is stable. And so, but now, as we were saying, since it is a semiconductor, when you increase the temperature, then you start seeing some carriers, right? You start seeing some what's called thermally generated carriers, right? There are just, and where are these carriers coming from? Well, in reality, once you start putting some heat into the system, then you start bumping some of these electrons out of the outer shells of the silicon atoms, and so they start coming out, and then when you end up here is a free electron that is moving around in a random manner, and then you have a hole, which is the hole that was left by that electron getting out of that shell, right? So that's a hole that is charged positively and is walking around. And that electron is going to go and bump another electron from another atom, and then that other electron is going to, at some point, is going to come fill that hole. You know, so you get electrons and holes moving around. But that's not that interesting. The case that is most interesting is when we have So let's draw something really quick. So this is what it will look like, right? As you start increasing the temperature. So you're gonna have some holes and electrons moving around in a random manner, right? But now the more interesting case is when we talk about doped silicon. Doped silicon, there is two types, right? There is a donor doped silicon and there is acceptor doped silicon, correct? So we'll talk first about donor doped silicon. As the word said, is silicon doped with donor atoms. Donor atoms are those that have an extra electron in their, more than silicon, in their outer shell, which means that it doesn't fit neatly into the silicon lattice crystal, right? So once you put it in, that electron is going to start to shift around. So now you have a what's called as a free carrier, right? In this case, an electron. So what you have is the following figure. So here's the lattice, but now we have added a phosphorus atom, right? So once we do that, then phosphorus has that extra electron that comes out, right? So now phosphorus is not neutral anymore, but it becomes positively charged, the atom itself, since it lost an electron, right? So you got a positive fixed charge because this atom cannot move, and we got an electron that can move freely around the lattice, right? So that creates what's called as an N-type material because it has electrons that are free to move. And you can think that if you keep increasing the amount of phosphorus atoms or the dopants that you put into this silicon, then you have more and more and more free electrons, and that's exactly what happens. So now you see all of these silicon atoms right here are neutral, right? So in reality, we don't care too much about this. We care about the fixed charges, in this case the positive fixed charge right here, positive fixed ion, and then the electron that just came out, right? That is free to move around. And so to do that, to just focus on those two things, we use a different model, very similar, but then it's the following. So this is the simplified model for N-type silicon, alright? So let's write that. And this is the one that we should remember when we're trying to understand things. And then, as we said before, is donor doped silicon. Again, because phosphorus donates an electron to the intrinsic silicon. And then, so some things that are good to know. When we see ND anywhere, it means the donor or electron carriers density. That is the number of electrons per volume or per cubic centimeter, right? So now let's expand a little bit into this model. Here we got what's called the positive fixed charges, and we have also a large number of mobile electron carriers that is proportional to the amount of dopants, of course. Right? And so the positive fixed charges are due to the phosphorus atoms that are now positively charged, that cannot move around, and then the electron carriers are due to that extra electron that phosphorus is donating to the lattice that can move freely around the silicon. And if you note here, there is a positive charge that can move. And so what that is some thermally, so remember this is the semiconductor, right? So it's heavily dependent on temperature. And so even though we might not want it, as we increase the temperature, and at room temperature there has to be some thermally generated mobile carriers. Right. And so due to charge neutrality, we do know, so the net charge in this material has to be equal to 0 because there is no applied field, right? So what that means is that the number of negative charges in this case electrons is always equal to the number of positive charges. In this case, these are the fixed positive charges plus any thermally generated hole. And these are holes, remember this. Right? And so as an important thing, this means that net charge is equal to 0, which is what we want. Now, following a similar model, actually very similar, we talk about p-type silicon. So the previous silicon was doped with donor atoms. Now this one is doped with acceptor atoms, right? So we say that is acceptor doped. Correct? Which means, will become clear in a little bit, that there are a large number of hole carriers. If we dope, for example, the silicon with boron atom, so if we take boron and we use it to dope intrinsic silicon, then boron has one less electron than silicon does in its outer shell, which means that it's going to accept one electron and basically it's going to introduce one hole into the lattice. So what that means is that we can dope silicon with acceptor atoms to introduce what I call as hole carriers, or you can also say hole mobile carriers. These are positively charged. Okay, so now let's again draw a simplified model. We'll use this model for understanding later on some concepts, so it's very important that we understand it. The simplified model. Again, since boron receives one electron, then it becomes negatively charged. So the atom cells we cannot move, or the fixed charge becomes negatively charged, and so this becomes what we call negative fixed charged. But it does release some positively charged holes which are mobile into the doped silicon, right? So what that means is there is a large number because the amount of acceptor atoms that you put into the silicon is usually pretty large. Okay, and then again you can see here that there is a thermally generated electron, which sometimes we don't want, but we'll have to do with that. This is the physics. So, semiconductors. And then something that we probably should keep in mind is N sub A, which it's simply just the acceptor or hole carriers density. So that's basically number of holes per cubic centimeter. Note again that for charge neutrality, the number of positive charges positive mobile charges, in this case holes, is always equal to the number of negative charges in this case that's fixed negative charges plus the thermally generated electrons. So in conclusion, N-type materials have, let's go, lots of electron carriers, and P-type materials have lots of hole carriers. Okay, so now we'll talk briefly about the two mechanisms that you can make, with which you can make carriers move around the silicon, or the mechanisms for carrier motion. And we're going to talk briefly about them. So that's going to be mechanisms for carrier motion. So basically there is two. There is one that's called drift, and it is motion due to an electrical field, and it's the one that we're more familiar with. To an electric field. And then this is so because if you remember, you got this equation that tells us that a charged particle, if you were to put it in an electric field, is going to experience a force that's going to make it drift along the path being guided by the electric field, right? Where the acceleration, this should be all in previous classes, I think. But the acceleration is given by the charge times the electric field over the mass of the charges. And now the other one, it's called diffusion. And that's the one that's going to play a pretty important role here. And so the idea here the particles tend to move from areas of high concentration to areas of low concentration. Right? In other words, particles' motion is driven by the concentration gradient. I will explain that in a little bit. First, so concentration gradient, what does it mean? So gradient in the direction points in the direction of maximum change in carrier concentration and the magnitude. Because let me write this out. Change in carrier concentration. Concentrations. Make a little graph here because I'm visual, so it helps me understand things. As you move a little distance, dx. So suppose we have the material where you have maximum concentration in this side. Actually, move this a little bit to the right. You have maximum concentration in this side, so the gradient vector will point in the direction of maximum concentration, right? So point in this direction, right? And the magnitude of it will be the magnitude of increase as you move a little. So here is the position, and here is dx, right? So it will point in the direction of maximum increase in concentration, which is this way, and then the magnitude of that vector will give you the magnitude of that increase as you move that little dx, right? So particles here that are located in this region will move in the opposite direction of the gradient vector. So they will move down this way. And you can see that from the equations if you look at it. So now particles move from basically all it is that particles move from high concentration areas into low concentration areas. And you can use the concept of the concentration gradient to make that more clear, right? The direction and magnitude of maximum change in carrier concentrations as you move a little distance dx is this one, right? And so the particles will move in the opposite direction of the gradient vector. So that's that concept. So now we understand a little bit about p-type silicon, n-type silicon, and we understand a little bit about two mechanisms for carrier motion, which are drift and diffusion. Now we want to know what would happen if you put p-type silicon and n-type silicon together. So let's take a look at that. Okay. So, I mean, this is the concept of PN junctions. Right, and then something that's very important, we'll tell the real story. We'll not give you just some formulas that we can plug some numbers in, because that doesn't make any sense. So, here's the real story. Okay. It's the real thing. Okay, so when you first put together the p-type material with the n-type material, there are large hole and electron concentration gradients. So let's write that out, and then in a little bit we'll draw the models that we have from before, and we'll totally see how that's possible, how that happens. So the initial state, right? So the first thing is that we'll have an initial state, right? And then that one will just be the p-type material with the free holes going around, and then we bring that one close to an n-type material with the free electrons going around. The initial conditions also tell us that there is a large hole concentration in this side, and there is a very low concentration of holes in this side, right? We also have that there is a very low concentration of electrons in this side, and a very large concentration of electrons in this side, right? So note the large differential in carrier concentrations, right? Hint, hint, diffusion, right? So let's write what's going to happen. Due to this large differential in carrier concentrations, opposite mobile carriers rapidly rush or diffuse toward each other, annihilating in a process that is called annihilation. They are annihilating each other, leaving a region depleted of mobile carriers, or a depletion region, which is what we hear people mention a lot. So let's write it down. I think that's how it is written, I'm not sure. Or a depletion region. So now in the final state we have the following. So as we hypothesized, the free electrons that were in this side diffused towards the left, while the free holes that were in this side diffused towards the right. And what that caused was annihilation in this region on any carriers, right? So next time someone tells you about PN junctions and depletion region, you can have a visualization of what's happening, you know? Okay, so that's the final state, and that's how we will see the PN junction from here on. So now let's talk about the PN junction characteristics. Okay, so now we redraw the same thing down here, but now the only thing we added was some names to this to these places where there is no more, where we start seeing some mobile carriers again, called W1 and W2, which kind of give you the width, the complete width of the depletion region, which is what we put there. Something to note here is that the depletion of carriers in the depletion region leaves a region of uncovered fixed charges, these ones right here. And so now we have a net fixed charge in each side of the junction. An electric field does develop, pointing from the positive side onto the negative side across the junction, which is a very important concept. So let's write that down. across the junction. And so let's draw what the accumulation of charge will actually look like. Okay, so here is the net charge density. As you can see, there is a negative charge density to the left of the junction, because we got those negative fixed charges due to the negative fixed charges, and we have a positive charge density to the right of the junction due to the positive fixed charges, right? And then, as you can see here, an electric field develops from the positive side, from the right side, which has the positive charges, over to towards the left side, which has the negative charges, which is normal. Now let's go a little bit more in detail. Okay, so now in more detail, this is the same graph that we had before right here, where we have the charge density, and then now the charge density is coulombs per cubic centimeter, right? So you're gonna have the negative charge unit times the acceptor concentrations, right, which is those the number of acceptor atoms per cubic centimeter, and then here you have the positive charge unit times the number of donor atoms per cubic centimeter, right? So that makes sense. And so remember, the direction of positive electric field goes from right to left. But however, here we're drawing the electric field pointing from left to right, which means it has to be negative. That's the reason why it is negative, right? And that's something that kind of confused me at first when I was trying to understand this. Now, there is something that is called the built-in potential that is drawn here in this graph. So, built-in potential. The built-in potential is the voltage across the depletion region from W2 over to negative W1. Also, the built-in potential is the work that you will need to do to move a positive charge up from this point, from W2 over to negative W1 across the depletion region. So if you have a positive charge, you'll have to do work to move it across these other fixed positive charges, and then the negative charges will be pulling you over to the W1 region. So here you have to do a lot of work, and as you get closer to the negative charges, you have to do less and less work until you reach the point. So the built-in potential is right here. So let's draw that. Let's write that out. The work needed to move a positive charge from W2 to negative W1 across the depletion region. Okay, so now we'd like to talk a little bit about diode operation, the diode device. And I like to call this section exploiting the junction characteristics that we discussed before. So again, let's draw what we had before with the different currents modeled, right? So what we have here is an electric field that we have explained previously, and then we have hole diffusion due to the holes being here in high concentration, and here there are no holes, and so in very low concentrations there is going to be hole diffusion from this region over to this region inside the depletion region. And then you're going to have electron diffusion due to the high concentrations of electrons in this side and basically no concentration in this side. Then you're going to have hole drift due to electric field pointing from right to left. And then you're going to have electron drift due to the electric field again. And then, so if you add those up, you're going to have current due to diffusion from left to right, and then current due to drift from right to left, assuming that the current is given by the flow of positive particles. Right, so the explanation for some of these things, let's write them down. So note, so as you can see, the current due to diffusion is equal to the current due to drift in opposite directions. They cancel out, and there is no current under no applied bias. So note, under no applied voltage conditions, the hole diffusion motion cancels with the hole drift motion and the electron diffusion This is analogous to saying that with no external voltage applied, to the PN junction, the diffusion indirect currents balance exactly, and there is no net current flow. Like we said before. Okay, so now we'll talk about diode operation under an applied bias, and then we'll talk about three cases. So and then we'll talk about three cases. And so the first one we'll call the equilibrium case. Okay. So let's draw that, which is just the conditions under basically no applied bias, or B bias equal to 0. And so it's basically what we had before, where the diffusion current balances the drift current, and then we have a total of 0 current flowing it, right? So the voltage across the junction is just the built-in potential that we had from before with no applied conditions. The total current is equal to 0 because the diffusion current and the drift current are equal and opposite. So the intuition, we'll just write that down really fast. across the diode is 0. So now we'll talk a little bit about forward bias. So forward bias, can't write, there you go. So let's draw the schematic. So here are the conditions and the results under forward bias. So we apply a forward positive voltage to the diode, positive forward voltage to the diode, and then we get that the diffusion current increases while the drift current decreases, which means that we get a total current that becomes positive, and we see that the depletion regions become smaller, which means that the voltage across the junction is going to be the built-in potential minus the forward voltage. So the intuition behind the forward bias case is the following. So when in forward bias, note that you are adding more holes to the p-type material and more electrons to the n-type material. The carrier concentrations increase. And thus the concentration gradient increases. And thus you get more diffusion current. Further, since some of the extra holes and electrons go on to fill the fixed charges, therefore the depletion region decreases in size. Therefore we see a reduced drift current. Visually, what we have is due to the forward positive voltage, we got more holes coming into the p-type material, right? So now the concentration in this side increases substantially, right? And in the other side, what you have is more electrons coming in, right? So what's happening is that the concentration differential, in this case, is gonna be, there's a lot of holes in this side and very, very little in this side, and so you get a lot of diffusion current going this way, right? And then further, since there are more holes, all the negative uncovered fixed charges in the p side are getting filled up by these mobile holes, right? Which means that the width of the depletion region is getting smaller. As the width of the depletion region gets smaller, the electric field magnitude decreases. and then the drift current is proportional to the electric field, and so since it decreases, the drift current decreases, and then we have a total current that points from left to right, or a forward current. Okay, so now let's talk about the reverse bias. So we are applying a reverse voltage or a positive voltage at the N-type material, right? The results are that we get a wider depletion region, that now the drift current dominates, right? And now we get a wider depletion region. This is also seen by the fact that the junction voltage increases, and then we get a total current that is less than 0, meaning it is flowing from right to left. However, I total is very small. That's something that we have to remember. It's very, very small. And so let's talk about the intuition behind the reverse bias. It's a little bit long, but we'll try to make it go fast. Now I'll explain it as I write it. So as you apply the voltage V reverse or VR, the extra holes in the p-type material flow into the negative terminal of the supply, leaving a greater amount of negative fixed charges. So as you can see, right, you get the holes in the p-type material that are free to move, going over to ground, and then uncovering another and then leaving other fixed charges behind, which makes the width of the depletion region in the p side increase, right? Okay. Now let's talk about the N-type material. The electrons leave the N-type material leaving the positive charges behind, leaving new positive fixed charges behind, and widening the depletion region. Further, since the carriers concentrations decrease, the concentration gradient decreases as well. And we have a reduced diffusion current. On the other hand, as the depletion region widens, the electric field increases as well. And then, you know, the drift current is proportional to the electric field, and therefore increasing the drift current by a small factor. So here's an interesting question. But if there are fewer carriers, what is drifting across the reversed biased PN junction, right? What is moving across if we have less carriers? I mean, it doesn't make any sense, right? So let's write that question down because it's very important. Actually, they are thermally induced carriers. This current, and this will lead us into our next topic, is what is called the leakage current. And in most times, it's a non-ideal effect of diodes. Something that we don't want. Alright, so now let's talk about the leakage current in PN junctions, or diodes. So the question here is, the first question is, why is it that reverse bias diodes don't really conduct? Right? And so, well, here's the story. So when the PN junction is reverse biased, like we had it just a second ago, the depletion region widens, as we saw, and any electron hole pair that is thermally induced, meaning because of an increase in temperature, or by a photon, meaning light, right? Remember, there is some electrons that are intrinsic to the semiconductor, you know, that are just going around in a random motion that we can't really get rid of. That, you know, and so if we increase the temperature, there are going to be more of those electrons, and then this huge field that is developed across the PN junction sweeps them across, and then you get your current, right? But if there is a photon, it also generates the same effect. So hole pair, thermally induced, is quickly swept away by the intense electric field across the PN junction. The current due to these thermal carriers is called, so the current what it called leakage current. So that's where it comes from. And becomes, in this case, the drift current. Right? However, here's a big point. However, note that leakage current is not really affected by reverse voltage it is only strongly affected, as mentioned before, by light and temperature. And so here we explain leakage current, and we explain why reverse bias diodes do not conduct. Okay, so now we will talk about our last topic in this video, which is the capacitance of a PN junction. So as can be seen from the depletion region, the depletion region stores charge. You know, there is some fixed charge in each side, and it has a potential difference across it. So it meets the characteristics for having a capacitance. Therefore, it must have some capacitance to it, right? So let's write that. So we know, as can be seen from the depletion region, these regions store charge and have a potential difference across it. Therefore, it must have a capacitance. This can mathematically also be seen by the fact that capacitance is equal to charge stored over the voltage across it. And there is charge stored, and then there's voltage across it. So it has to be capacitance. For example, let's take the case of a reversed biased junction. So now let's note that as we increase, so let's write that as we increase the reverse bias voltage, VR, more mobile electrons exit the N-type material, and the depletion region extends further. We know that simply because we have a positive voltage at this side. The electrons are going to be attracted to it, so they're going to be exiting this terminal, and are going to be leaving more fixed charges behind, which is the next thing. So leaving more fixed charges behind. We also know that simply seeing that capacitance is equal to the change in charge, the change in voltage, we can see that as we increase the voltage, when you increase the voltage, you have more fixed charge now. So you increase the amount of charge that is stored in the depletion region. So Q increases, and the capacitance remains constant. Or does it? So let's see, let's keep increasing it and see what happens. So what happens as we increase the reverse voltage even further? So we can see that the number of electrons available in the N-type material starts to become very low, right? As we started like pulling all these electrons out of the N-type silicon, there's only going to be very, very few, right? So pulling them is going to be a lot harder, so we have to increase the voltage even further to get them out of there. And the N-type material starts to become very low, and the depletion region can't extend any further, right? You can't pull it farther than it is the physical size of the device. And if there are no more electrons to get out of that material, then you can't extend it any further. What that means, meaning that the change in V reverse did not uncover new fixed charges, right? So there is no change in charge stored. And thus we have a nonlinear capacitor, right? Since if we had a linear capacitor, if we kept increasing the voltage, we should see more charge and more charge being stored, so that the capacitance remains equal. But that's not the case. As we increase the voltage even farther and farther, the charge stored doesn't change at the same rate, right? So we have a nonlinear capacitor. And thus, graphically, it will look something like this. So here is how it looks graphically. Here's the linear region where it acts just like a linear capacitor. You increase the voltage, the depletion region widens, you have more charge stored in the depletion region, and therefore, you get the linear curve right here. But then later on, you start increasing the voltage, and the change in the charge stored starts to be very little, right? Because basically the number of carriers are being very, very small now, right? So you can't store any more charge in the depletion region, and then you can't uncover any more fixed charges, just like it says here, right? So it starts to flatten out as we approach a limit, right? And so it becomes a nonlinear capacitor. Okay, and so that's basically what I wanted to say about PN junctions. The PN junction and diodes. The next video will cover a little more about MOSFETs and their operation. So we'll kind of bridge the gap between this video and the next one.